Continuing our discussion on nonlinearities in RF systems, the next topic we're going to discuss is gain compression. So what is gain compression? Now, if we look at the response, we talked about for a third order nonlinear system, we saw it was something like this. And we noticed that the fundamental frequency had a coefficient of alpha 1 a plus 3 alpha 3 a cube by 4. So this was the coefficient of the fundamental frequency. Now, as we discussed in the previous slide, if we want to look at the gain for the fundamental frequency, we just take this a out, and then we have alpha 1 plus 3 alpha 3 a squared by 4 times a cos omega t, right? So this is this is nothing but xt. So this term then, let me change the ink. So this term in this box, this term is gain for the fundamental frequency. Or the fundamental tone. Okay. Now, this component alpha 1 plus 3 times alpha 3 a squared by 4, it can behave in two ways and that depends on the signs of alpha 1 and alpha 3. Now, if alpha 1 and alpha 3, if their product is greater than 0, right, which means that one of them is positive and the other one is negative, then we'll have y of t expanding as a increases. Okay, so if alpha 1 times alpha 3 is greater than 0, right, then y of t expands as e expands. Okay, which means that as the amplitude of the signal increases, the output also increases, right? And a very simple example would be an ideal BJT in the forward bias region. Okay, so if we look at this, so this is your y, this is your output, and this is your input. Okay, let me clear the screen. So this is your output, this is your input, and what happens is that if you do an expansion of this, if you do an expansion of e to the power x, right, then you'll find that this IC, it proportionally increases with VBE. So as long as VB increases, you'll see IC always increases, because this expansion has all the terms positive and all the coefficients are also positive. So the product is always greater than 0. Now, typically in RF systems, that's not the case. For typical devices, now this was an ideal BJT, right? For typically what happens is that this product is less than 0. You'll see that in all active devices, you'll find this product to be less than 0. And then what happens is that this gain, right, the gain for the fundamental, this gain, which is alpha 1 plus 3 alpha 3 e squared by 4, right? This is the gain. So this gain, it decreases with a. Why does that happen? That happens when alpha 1 times alpha 3 is negative. Okay, so if it is negative, for example, if alpha 3 is negative, you'll have something like alpha 1 minus 3 alpha 3 mod of alpha 3 and e squared by 4, right? So as a increases, right, this negative sign makes it small, then your overall gain starts to decrease. Okay, so that's the case with that's the case when alpha 1 and alpha 3, their product is negative, and in this case we say that the gain is compressive. In the first case where it was increasing, it was expansive. In the second case, it is compressive. And typical RF systems, they behave in a compressive manner. So what happens is that as you go on increasing the amplitude of your signals, the gain, it does not stay flat, it goes on decreasing. So if I look at gain with respect to amplitude, you'll see that at higher amplitudes the gain starts to fall. So this is a typical behavior you'll see in RF devices. And this falling of gain, it's called gain compression. Okay, so that's where the term gain compression comes from. Okay, so how do we characterize this point? So how do we sort of quantify this, and if we have to compare two devices, and if we have to say one has more gain compression than the other, then how do we quantify this quantity? The way to do that is we look at the 1 dB compression point. 1 dB now what is a 1 dB compression point? The 1 dB compression point is the point where gain compression, so it's the input power where gain compression is equal to 1 dB. So gain compression topic, this is it's a quantity which is typically described for amplifiers. Now the gain compression point, the 1 dB gain compression point of an amplifier is a point where is the input, okay, is the input power at which the gain at output has compressed by 1 dB. So what you're doing is you are increasing the input power, and you're looking at gain, and for low input powers the gain is almost flat, but as you go on increasing the input power, you'll see a dip in the gain, and the point where this dip becomes 1 dB, that point will be your 1 dB compression point. So that's your 1 dB compression point. Okay, now we can talk about this in terms of voltages as well. So we have this relation And in this relation, I can say that the okay, if I take this A out, this is A cos omega t. Okay. So this is the gain term, right? So the point where this gain G, this gain G is 1 dB smaller than the small signal gain, right? When I drew this graph where P in and G, so this area where the gain is flat is the area where P in is very small, that is the input power is very small. And if the input power is very small, then the amplitude of the input signal is also very small. And we know that if the amplitude of the input signal is very small, that corresponds to a gain of alpha 1, which is the small signal gain. So what we are saying is nothing but the 1 dB compression point is the compression point at which the gain expressed in dBs. So this is how we express it in dBs, right? We do a 20 log since we are talking about amplitudes and not powers in this case. So a 20 log and then gain is equal to the small signal gain minus 1 dB. Okay, and if you calculate a 1 dB, the input amplitude in this case, it comes out to be this. So the 1 dB compression point is the point where the input amplitude, the amplitude of the input signal is equal to under root of 0.145 alpha 1 by alpha 3. Okay. Now it changes the value of A in changes based on the values of A alpha 1 and alpha 3 for different systems. Okay. Now if we calculate this change in terms of absolute values, since 1 dB compression is in the dB scale, if we do it in the absolute scale, we'll find that it represents a 10% reduction in the gain. So the 1 dB compression point represents a 10% reduction in the gain. And we talked about this in terms of amplitudes. We can also express this in terms of power, as I mentioned in this case. So this would be the explanation in terms of power. We can do an equivalent analysis in terms of power, and as we did for as we expressed this in terms of input, we can also do this in terms of output powers. And you simply have to multiply it by that particular gain factor, or if you're working in the dB scale, you simply have to add the gain in dBs and you can get the corresponding output at which the compression is 1 dB. So you can express it both in terms of input powers as well as output powers. Okay. Now, what is the effect of gain compression on waveforms? Now, if we look at frequency modulation, if it's an FM signal, right? So all of your information is stored in your phase, right? So all of your information is stored in your phase. Now, even if your amplitude changes, your information does not change because it's stored in your phase, right? So any change in amplitude, it might lead to gain compression, but eventually your information is still stored. So there is no issue. So FM is immune to gain compression. But amplitude modulation severely, it highly depends on the amplitudes of the baseband signal, right? That's how it's being modulated. So in this case, if the system for a certain amplitude of the AM signal, if the system goes into compression, then the output would not be the required output, right? Since the information is stored in the amplitudes, that particular amplitude will have been compressed in the output, and it will not reflect the actual modulated signal, the actual amplified modulated signal, but it will have changed the information contents of that signal. So amplitude modulation, AM based signals, are very susceptible to gain compression, and it can lead to data corruption if gain compression is present in a system which is based on amplitude modulation. Okay, a related effect is called now gain compression can lead to some detrimental effects in systems, and one of the biggest ones is desensitization. And what is desensitization? So desensitization is nothing but a very high large magnitude, say a large magnitude interferer, right? A large magnitude interferer which arrives at the receiver along with the desired signal, although both of them do not have the same frequency. So if this is f naught, this might be f naught plus some delta f, it will be at a different frequency, but the amplitude of the signal is so high that it drives the amplifier, or it drives the receiver into gain compression, and that creates problems. So again, let me repeat what desensitization is. It is the effect where an interferer, a large signal interferer, desensitizes the receiver. That is, it drives the receiver into gain compression, and then the receiver is not able to properly receive the desired signal. Okay. Now let's see mathematically what happens if I have a signal. I have a signal x of t. So let me say I have an antenna, then it goes to an amplifier. Okay, that gives me y of t, and this is my x of t. Now typically I receive a1 cos omega 1t. This is what I typically receive, but someone wants to disturb my system, and what he does is that he sends another signal, a2 cos omega 2t. Okay, so typically I receive this a1 cos omega 1t, but now someone sends a2 cos omega 2t, where a2 is a very high amplitude, so it's a high power signal at a different frequency. So someone sends it along with my desired signal, and I receive it through the antenna. Now it goes to drive my amplifier. Now what happens is that if I look at the third order characteristics, the output looks something like this. Okay, now if you do the maths, you will see that the fundamental tone for omega 1t, okay, for omega 1t, I'm not talking about omega 2t, even for omega 1t, the output, the gain would be a term which looks like this. Okay, the gain would be a term which looks like this, and now in this we can see that there is the typical alpha 1 plus 3 by 4 alpha 3 a1 squared, but there is another term which is this 3 by 2 alpha 3 a2 squared, right? And now if your a2, which is your interferer, if the amplitude of your interferer is much larger than your desired signal, then the gain of the fundamental frequency. Now the gain which this amplifier presents to the fundamental frequency omega 1, right? So that gain will now decrease based on the amplitude of A2. So this gain will start getting compressed because of A2, not because of A1. Typically what happens in gain compression is that the signal itself leads to compression, right? But in this case, the desired signal has an amplitude which does not drive this amplifier into compression, but another signal, which is an interferer, its amplitude or its power drives this amplifier into compression, and as a result we are not able to get the desired gain for our desired signal. Okay, so this is how gain compression affects real life systems, and this process whereby an interferer leads to the gain compression of a desired component, this is called desensitization of a receiver. So you'll see that sometimes in some places you'll have those blockers where you're not able to receive any signal, right? Your phone networks are jammed. So this is exactly what's happening. A very high power signal is being delivered, and that saturates your receivers. If your receiver receives this omega 2, that is, it is within the pass band of the initial filters from the antenna, because usually the first block after the antenna is some sort of a filter, right? And if that filter allows this omega of the interferer, then your amplifier is definitely going to be desensitized. So whenever we use blockers in some high security places, then all that is happening is the same principle of desensitization. Okay, let's look at an example. So if we have a 9 megahertz signal, a 900 megahertz GSM transmitter, which is delivering a power of 1 watts to the antenna. Now, by how much must the second harmonic of the signal be suppressed so that it does not desensitize a 1.8 gigahertz? So the second harmonic of a 900 megahertz signal would be a 1.8 gigahertz, right? And okay, how much must the second harmonic of the signal be suppressed so that it does not desensitize a 1.8 gigahertz receiver having a P1 dB of minus 25 dBm? Assume the receiver is 1 meter away and the 1.8 gigahertz signal is attenuated by 10 dB as it propagates across this distance. Okay, let's understand the problem first. So the problem is that I have a cell phone, for example. I have a cell phone, and in this cell phone I have an amplifier which drives an antenna, right? And then this cell phone gives out some signals. Now the signals which are given out by this cell phone have two components. If it was an ideal system, it would have just one component, that is this one, the 0.9 gigahertz or the 900 megahertz one. But because it's a non-ideal system, it's a nonlinear system, it also generates a second harmonic at 1.8 gigahertz. Okay, then it transmits it. Now there is another phone which is trying to receive signals. Now the receiver of this phone has a 1 dB compression point of minus 25 dBm, right? So if an input signal of minus 25 dBm comes in, then this device, the receiver of this device, will be at the 1 dB compression point, right? So we have to ensure that this 1.8 gigahertz signal should not be higher than this limit. So we have to see how much should we attenuate this at the source so that it does not impact the performance of this receiver at 1.8 gigahertz. Okay. Now the power transmitted at the source of this cell phone is 1 watts. So mentioned it's 1 watts, and that corresponds to 30 dBm, right? Now the 1 dB compression point of the receiver, this receiver has a 1 dB compression point of 25 dBm, minus 25 dBm, and the attenuation in path is 10 dB. So we generate 30 dBs. We generate 30 dBm, sorry. We generate 30 dBms at the source, and there's a 10 dB attenuation. And we require that the input should not be the 1.8 gigahertz, right? This band, the input should not be higher than 25 dBm, because otherwise it will drive this receiver into compression. And it's separated by, it is separated by 1 meters, and in that 1 meters there's a loss of 10 dB, which means that in order for this signal to be minus 25 dBm at this point it should be minus 25 dBm plus this 10 dB, so that is minus 15 dBms, right? So this 1.8 gigahertz signal at this end should not be more than minus 15 dBm. Otherwise, it will be higher than the 1 dB compression point of this receiver, and it will drive this receiver into compression. Now, what does this mean? This means that the second harmonic, where should the second harmonic be with respect to the fundamental? Okay, so if we look at the fundamental in this case, which is 900 megahertz, this is at 30 dBms, right? And the second harmonic should be minus 15 dBms. I don't know, maybe like this, although it's not the correct representation, I'm just pictorially showing it to you. So the second harmonic in this case should be 45 dBs, right? This 30 plus this minus 15, so 45. So it should be 45 dBs less than the fundamental frequency, the power delivered of the fundamental frequency, which is 30 dBm. So the second harmonic should be 45 dB less than the transmitted output power at the fundamental frequency. Let me clear this and let me repeat in a summarized fashion. We want that the received power at 1.8 gigahertz should be minus 25 dBm or lower. There is an attenuation of 10 dB, which means that the delivered power at 1.8 gigahertz should be less than 15 dB, minus 15 dBm. We also know that the transmitted power is plus 30. So this power for the fundamental is 30 dBm. And we also know that this power should be minus 15 dBm if we don't want the receiver to be driven into gain compression, which means that the second harmonic should be 45 dBs less than the main carrier signal. Okay, it should be 45 degrees less than the fundamental frequency.